All right, hello. Welcome to video 1 of 4 on kind of this Ohm's Law section of our circuits part. Ohm's Law is a hugely important part of understanding electronics. It is potentially the most important part of understanding electronics, the foundation of understanding how electronic circuits work, and it involves 3 different parts. And so I'm going to cover those parts, and a lot of these terms you've probably heard before, may not understand them. Hopefully through the end of this, you'll have an intuitive understanding of what each of these are. So the things that we're going to cover: voltage in our first video. The second video, we're going to talk about resistance. Third video, we're going to talk about current. You're going to understand intuitively what each of these things mean. And then in the fourth video, we're going to bring them all together to form Ohm's Law, which describes how these things interact with each other. All right, let's get on with video number 1. Okay, so first of all, what is voltage? Well, voltage can be described in a number of different ways. So voltage is electrical potential or electromotive force or electrical pressure. Electrical pressure might be a good way to think of it, but more commonly people are going to be calling it electrical potential. And if we want to talk about electrical potential, we need to review our different kinds of energy here. So we have potential energy and kinetic energy. So potential energy is energy that could be expended, but it's not currently being expended right now. So an example is a cup sitting on a high shelf. Kinetic energy, on the other hand, is a cup falling off of the shelf, essentially energy that is being used as we speak, energy that is currently being used. So generally with circuits, we're looking at circuits at an instant in time. So we're usually going to refer to voltage as potential energy or the electrical potential, not necessarily potential energy. So electrical potential. And if we want to get a grasp of kind of how this works, we can think about, well, generally in any conductor, we have an atom. And I'm just going to draw a nucleus here of the atom and a very simple electron on the outside. So we have a nucleus and then we have an electron. And this electron is floating around out here somewhere. This is, I believe, a hydrogen atom that I've just made, but you can scale this up to a bunch of different things. And conductors are going to have electrons that are called free electrons. So maybe they have an extra electron here, and it likes to pass between, or it relatively easily passes between that atom and another atom. So it can kind of get into these orbitals or these shells around these atoms. And that's all electricity is. It's these electrons, and these electrons are moving from one atom to another. And voltage, in this case, is kind of a measurement of how hard are we pushing on this electron in the first place. So how much are we trying to get this electron to move from this atom to the next atom? So that's why electrical pressure is kind of a good way to think of it as well. And often, especially in these beginning parts, we use a water analogy. So it's very analogous to water. And in terms of water, we can imagine that maybe we have this big trough of water up top here, and we have some water column. And essentially that water column, we have a bunch of water up here. Remember, potential energy is the work that could be done, but is not currently being done. And if we measure this at an instant in time, we can look up here and we say, okay, we have gravity pulling down this way. So there's a force, and that force is pulling on this water, and that water is then creating pressure. So if we were to measure the pressure of this water, if it was up here, it'd be relatively high pressure. If the water was only up to maybe this level, it'd be a lower pressure, but still generally kind of high. If we only have water up to here, then that's not going to be a very high pressure. So we have pretty low pressure there. And this is kind of analogous to our voltage, and that is how hard are we pushing. So if I have a really tall amount of water here, then the pressure down here somewhere is going to be pretty high. If I only have water up to here, then the pressure in that same spot is going to be pretty low. So we're essentially thinking about how hard are we pushing on these electrons, and that is voltage. It's all voltage is. How hard are we pushing these electrons and trying to get them to flow through this circuit? And if you want to think of it, another useful way to think of it is maybe like ping pong balls. If you had a pipe full of ping pong balls, let me see if I can draw this pipe here. So we have a pipe, and in this pipe, we have a bunch of ping pong balls next to each other. And we're trying to push these ping pong balls through that pipe. That's all voltage is. It's a measurement of how hard we're pushing. And now something that we should mention, and if this confuses you, just ignore it. This is just kind of a quirk of voltage, is voltage doesn't have to mean that the electrons are moving. We can still have voltage, or we can be pushing on something without it moving. It's the same thing as if I'm pushing on a wall. Then that wall doesn't want me to let it move, or it doesn't want me to move it. So I can be pushing all I want, which is kind of an equivalent of high voltage, or a high-ish voltage, some voltage, some push, some force that I'm exerting. But that wall doesn't necessarily have to be moving. And we're going to talk about why that wall might not move, or why these ping pong balls might not move through this tube, or why this water might have a hard time flowing through this pipe. And that is going to be our second video called resistance. So we are going to cover resistance in the next video. I'll see you there.